The moment we've been waiting for. Doing calculations using the equilibrium constant. Now, usually these problems are broken into a few different parts, and that is we find out the initial conditions, we use the stoichiometry to determine the change, and then we can use those two pieces to find out what would happen at equilibrium. And often these are called ice tables for initial change in equilibrium. And so let's write out our ice. Initial, change, and equilibrium. And what we'll do is we'll take the initial portion, add it to the change to get our equilibrium. Now, let's say that we begin this problem with 0.5 molar COBr2. So we initially in our flask have 0.5 molar COBr2. And let's also say that we don't have any carbon monoxide in there. So we have 0 of that. And let's say we have no bromine in there as well. Now, the question is, what is the concentration of each of these species at equilibrium? Now we have our K, it's 0.190, and so we should be able to solve this. Now, at the beginning you might not know how to approach this, but this is a very systematic way of solving these problems. So, step 1, write out ice here and write out all of the information that we have. Some problems they'll start off with just the initial conditions, and some problems may indicate some concentration at equilibrium, and then you can just write in numbers down here. In this case, we don't know what those conditions are at equilibrium, so we'll have to move forward without that. Now, for change, we do not know how much of the COBr2 is going to become carbon monoxide and bromine. But we should expect that we will make some products because we have all reactants and we have no products, so we must end up making some in order to get K to 0.19. So we look at the stoichiometric factor here, and there's 1 there. So let's say we use up X amount of COBr2. Now, if we use up X amount of COBr2, we'll make X amount of CO because our balanced chemical equation is 1 to 1 to 1. So we would just write plus X over here and also plus X there. Now, it's not actually important to know which direction the equilibrium will go. We do know it's going to go forward because there's none of this in there. But if we weren't sure, we just need to make sure that we put negatives for the reactants and positives for the products and then go from there. And all of the math will work itself out even if it goes the other direction. Just to make sure that these two are on the opposite sides of the reaction, have different signs. So that way the reaction is going that way or it's going that way, won't matter. Now, to calculate what's actually going to happen at equilibrium, we just simply add the initial conditions to the change, and then that will be what happens at equilibrium. So down here we have 0.5 minus X, so add these two together, minus X. And here 0 plus X, that's just X, and 0 plus X, that's X. Now, what do we do next? Well, we'll need to put this in another equation that relates it to the equilibrium constant. So let's write down the equilibrium constant expression. And K is carbon monoxide concentration. and times bromine concentration divided by concentration of COBr2. Right? So this is K. And we know the value of K, and we know kind of the concentrations at equilibrium. For COBr2, it's 0.5 minus X. For CO, it's X. For Br, it's X. So let's plug those in to our equilibrium constant expression, and let's also plug in the value of K. So 0.19 equals concentration of CO, that's X, and then we're going to multiply that by the concentration of Br, that's also X, and then we're going to divide by 0.5 minus X. Now we just need to solve for X, which admittedly is a little bit annoying in this case because we need to use the quadratic formula, but I'll go through that for you here. So this is just X squared on top, and then this is 0.5 minus X. So let's multiply 0.5 minus X over to the 0.19, and then we'll have X squared over here. So 0.19 times 0.5 minus X equals X squared. And then we'll need to distribute this. So 0.19 times 0.5 is actually 0.095. And 0.19 times minus X is minus 0.19X. And that all equals X squared. Now we're going to want to move all of these over to this side so that we can use our quadratic formula. So that is going to look like this. 0 equals X squared. Let's see here. Plus 0.19X minus 0.095. Now this can go in our quadratic formula, and I'll just write that out quickly down here. Let's see here. Negative B. Now the formula says plus or minus, but if we put a minus in there, we're going to get a negative number out for concentration, and negative concentrations don't make sense, so we really only have to calculate the plus version of this. Square root of, let's see here, B squared minus 4 times AC, so 1 times C all over 2 times A, which is just 2. And if we solve that out, we should get, I'll write it over here, X is equal to 0.2275. Now that we have X, we can calculate the concentrations for each of these at equilibrium. And since X is the concentration of carbon monoxide and bromine, we can simply just write that down. So concentration of CO equals concentration of Br2 equals 0.2275 molar. And then we can just plug in X in here and figure out the concentration of COBr, which is just 0.5 minus 0.2275. And that will equal 0.2725 molar for the COBr2. So that's how to use an ice table. Now, you might wonder how we're able to use concentrations here. Well, since everything is in the same container, you can actually treat concentrations just like they're moles. And so I generally just leave these as concentrations because the concentrations are what needs to go in the equilibrium constant. So we just put that in and then calculate, and it's just like you're operating in moles, but it's actually molarity. So this is how to use an ice table to solve a problem. Admittedly, we did have to use the quadratic formula to do it, but that is an introduction to ice tables.